When we are designing a two-way communication system, one of the important parameters that we have to consider is the link budget. So in this video, we are going to explore what is meant by link budget and what are the factors affecting the link budget and why it is so important while designing the communication systems. So when we have a TX-RX communication system. So this is our TX antenna and this is our RX antenna. If you have a communication system in between these TX and RX, this link budget actually answers, will our signal from this transmitting antenna will be reaching on the receiver. That is what link budget says. So link means the TX to RX communication channel, and budget means whether it is has enough power to reach on the receiver. That is what it is, link and budget. That is meant by link budget. So let's try to understand it based on some analogy. Here I am going to consider an analogy based on a monthly financial planning, because we know that budget is a common term that we usually used for the financial planning, right? So I'm going to take that same scenario to explain it better. So let's assume that these are my earnings. So I have different types of incomes and I have this much earnings in a month. And if this is my expenditure, so I'm not going to spend all of my money on everything. I'm trying to spend only less. Then at the end of that month, I will be having enough balance and I'll be happy because I have enough balance, because my expenditure is less and my earnings are more. So let's consider another scenario. If I have this much earnings and but my expenditure is more than my earnings. So at the end of the month, not be having any balances and I'll be like bankrupt. I don't have nothing. So this similar scenario also work for our communication system. So let's see how that is happening. So in a two-way communication system, we can say that the money that we are considered here is the power. That is what the transmitting antenna is transmitting and how much power it is getting on the receiver. So the money corresponds to the power. So let's say that if this antenna is transmitting some power, and that is my total earnings, and I have some expenditure, right? So here this type of expenditure corresponds to the loss in this link. So if I consider all the losses which is happening from the transmitter to the receiver side, what is remaining, that is the balance corresponds to the received power. That so our financial analogy also corresponds to this transmitter receiver link budget. So here you can see that we have to consider the power, that is our total earnings or the total power from the transmitter system, and as it is going through the receiver, it will be facing different types of losses. So after all the losses, whatever is going to receive here, that is our balance, correspond to the received power. This analysis in this communication system is known as link budget. So we are trying to analyze what power will be receiving on the receiver after all these type of losses on the transmitted power. That is actually link budget. So link budget is an important phenomena when we are trying to design any communication system. So if you are trying to figure out any satellite communication system, cellular network, 5G planning, Wi-Fi and point-to-point communication system, link budget forms an important parameter. So let's see how the link budget or the received power on the receiver system is calculated. So this is our TX and this is our RX system. So we are considering line of sight between the TX and RX system. So, so the PTX is the total input power to this antenna, and we know that it has to go through the cable to the antenna. So there is a cable loss, and we know that antenna itself has a gain, so it has a directional pattern, and the gain is GTX. So the total transmitted power from this system will be PTX minus LTX. These LTX corresponds to the cable loss and other connector loss from this input to the antenna, and the GTX, this is the gain of the antenna. So this is the total power from the transmitter system, and it has to go through the air in between the TX and RX system. So when it is transmitting from the TX to the RX, we know that there will be free space path loss. So this free space path loss is the loss of the signal strength that occurs when an electromagnetic wave propagates through the free space with no obstacles, no reflections or absorption. So this is an ideal consideration. So we are considering there is no obstacles between the TX and RX system, and there is no reflection and no absorption. That is the free space path loss. So this name implies that. So that free space path loss is given by 20 log 10 of 4 pi d by lambda. From this, we can see that as it is directly proportional to the frequency. That means that at higher frequency, the free space path loss will be very high. And it is also proportional to the distance. So let's consider the case if D is equal to like 10 kilometers, and if the frequency is like a Wi-Fi 2.45 gigahertz. When we calculate this free space path loss, it will be around 120 dB. So here you can see that this value is very high. So this free space path loss is usually called as the budget killer because it is actually taking lots of power loss. That is why it is known as the budget killer. So after this much loss, that is, it has included the path loss also, and it is getting received by the receiver system. So this antenna also has a gain, which is GRX, and when it is received on the antenna, it has to feed onto the receiver system, so it has a cable loss. So after all these losses, it will be received on the receiver system. So the total received power will be including all the gains and all the losses. Here you can see that it consists of the PTX, then cable loss, then the antenna gain, then free space path loss, then the gain of the receiver and the gain of the cable loss. So this is the total received power. So this power gives an indication about how much power is received on our receiver system. So if this received power is greater than our receiver sensitivity, we can say that link is successful. That is, that it indicates that enough power is received on the receiver antenna system so that it can detect that as a signal instead of a noise. Then we can say that the link is successful. This is how we are calculating the link between a transmitter and receiver system, and we are making sure that whatever changes has to be made on different components. So based on these link budget, we may have to make some changes on the cable loss, that is shortening the cables and improving the gain of the antenna. So these sort of things that we have to consider based on these link budgets. So link budget is an important parameter that we have to be considered while considering a TX and RX communication system. So it is an important parameter. So this is a summary and means this is a simple block diagram showing the TX, cable, antenna, path loss, receiver, antenna, cables and the receiver, and this is our receiver sensitivity. So when on the starting, it will start with a TX power, then the cable will be producing some losses. So this is the loss. Then this power will again getting increased due to the gain of the antenna, and then free space path loss comes. So because of the free space path loss, the power will be again decreased. Then this antenna will be having some gain, and because of that, it will the power will again increase, and then we will be having the cable loss, and then power will be again decreased, and we will be having the total received power. So if this received power is greater than the receiver sensitivity, so this is the receiver sensitivity and this is our received power. If it is more than receiver sensitivity, we say that the link is successful. So let's consider an example scenario. So it is given like transmitted power is 20 dBm, cable has a loss of minus 2 dB and transmitted gain is 40 dBi, path loss is minus 114 dB, receiver antenna is plus 14 dBi, receiver sensitivity needed is minus 85 dBm. So we have to calculate the received power based on this, and we have to compare that with the receiver sensitivity. If this value is more than the receiver sensitivity, our link budget is successful. So based on this, we can calculate by adding all the gains and subtracting all the losses. So here you can get the value as minus 68 dBm, and as we know that the receiver sensitivity is given as minus 85 dBm, so this value is greater than minus 85 dBm by a factor of 17 dBm. This means that we have an excellent communication link between the transmitter and the receiver. This is how we are using this link budget information to calculate whether our link is successful or not. So the link budget that we have calculated is based on an ideal condition. In that case, when we are considered the free space path loss, we didn't consider any obstacles, reflections, or absorptions. We say that there is a clear path between the transmitter and receiver, but in actual case there may be lots of obstacles in between the TX and RX, and there will be lots of reflection and absorptions happening. So in actual scenarios, like we have to consider all these effects, so it is like a complex calculation. So let's see what are the other parameters which will be contributing to the link budget. So let's see. First one is fade margin. So these are due to the reflections and multipath impact. So we usually take around 20 to 10 to 20 dB margin for these fade margin cases. So let's see what are the factors influencing these things. So if you have a channel between the TX and RX, there will be loss due to the atmospheric conditions like rain, fog, etc. And if we have these type of trees and other objects coming in between the TX and RX, there will be loss. And if there are any buildings coming in between these TX and RX communication system, there will be multipath impact, and this will also cause the loss. So these all corresponds to the fade margins. So we usually consider around 20 to 10 to 20 dB margin for these cases. Other factors are antenna misalignment. Because of this, there will be some loss. And we know that if the polarization of the antennas does not match, it will also cause the polarization loss. And this will also correspond for the link budget. And next one is obstacles in Fresnel zone. So this Fresnel zone does not relate to to the far field region. This is something different. So this will be happening when we are considering a TX and RX communication system. This Fresnel zone is the ellipsoidal region that we have to consider in between the TX and RX, because when we are considering a TX and RX system, even if it is line of sight, like if you can see both these are on line of sight, we know that the wave from this antenna is not passing like a straight line. It is like based on the antenna radiation pattern, it will be propagating like this, right? So it is not like a straight line. Because of these type of spreading of these antennas, we have to consider an elliptical region in between the TX and RX, not like a straight line of sight. So this elliptical region that we have to consider in between the TX and RX is known as the Fresnel zone. So if any objects come in between these Fresnel zones, this will also contribute to some loss. So this will also impact the link budget. So these are some of the factors that we have to consider while calculating the link budget. As it is a very complex scenario, sometimes we may have to like over calculate the link budget based on these scenarios and have to assess whether our link is successful based on the received power. So I hope you get some idea about what is meant by link budget and what are the complications associated with the link budget calculations and what are the factors to be considered what, to included in calculating the link budget. I hope you get some ideas. Thank you for listening. If you find any of our videos useful, kindly support by liking, commenting, sharing and subscribing. Thank you.